So the second problem with our artificial diffusion approach is something that we call variational inconsistency. And that's something that I'll first try to illustrate and highlight for a few minutes to motivate as to why this is a problem. And afterwards, we'll try to fix it. So here we have essentially the two different approaches so far. We have our standard finite element approach, the Galerkin approximation, where we simply take the weak formulation of the partial differential equation and then we substitute or we replace the H1 spaces by these finite element spaces, and thereby getting these H's here as illustrative of the discrete nature of our solution now. Now we found that is actually a very unstable type of numerical approximation, and that's why we started fixing things by introducing now an artificial diffusion and specifically a streamline artificial diffusion, and thereby adding this term here. Right? That's what we did in the last two series of the last two videos. So there's a bit of a problem now going from the Galerkin approximation to the streamline artificial diffusion formulation that we have here. So suppose that we have as a true solution, phi true, something that we can actually obtain in our finite element grid. So suppose that phi true can be phi h. So what might something like that look like? Well, a very relevant example is if we have a flow through a tube, and if the velocities are sufficiently low, then we might obtain a solution that is actually quadratic. That's something that you might be familiar with if you've taken some fluid mechanics courses. So you get a flow that is quadratic through that tube. So if you would now use a finite element method to obtain a solution like that, you would use quadratic basis functions, and then we would be able to obtain the exact solution with our finite element method. And in that sense, we can write here that the true solution can be represented by phi h, or the other way around, phi h can represent the true solution. And if that is the case, then our Galerkin approximation will give us that solution. Now, the reason for that is that the true solution satisfies this rule, by definition of it being the true solution. It actually satisfies that rule for all possible choices of test functions W. So also certainly the couple ones that we choose in our finite element approximation. And given that this is a coercive formulation, it will permit one solution, it will permit a unique solution, so that solution will be the true solution. Now, okay, so the key point here just being that if our finite element space, if the true solution can be represented in the finite element space, then the Galerkin approximation will give us that true solution. Now the same thing can, however, not be said about the streamline artificial diffusion approach. We've changed the physics, right? We've added a diffusion, and thereby we would no longer obtain the true solution even if we could. And that's also pretty clear, because if the true solution satisfies this rule, then that means that this one is balanced by this one, which would mean that this one has to be 0, and well, it is not 0, right? So this is no longer consistent with the true solution, and that's what we call variational inconsistency. So to write that down explicitly, this one no longer, this weak statement, this weak formulation is no longer satisfied by the true solution. So if I were to substitute phi true in here and in here and in here in there, then this is still satisfied, but this is not satisfied. And that is what we call variational inconsistency. So let's look at an example and see that this is in fact the case. So I'm still using the same domain here, right? Something that we've used for a couple of simulations so far. But now I'm changing my true solution. And I'm changing my true solution by actually changing, by adding a right-hand side forcing. So now I've changed a right-hand side force, f, in such a way that the true solution is this polynomial function. So given that the true solution is simply a second-order polynomial everywhere on our domain, a Galerkin approximation with second-order basis functions can precisely represent the solution. And in fact, if I solve the Galerkin or solve the finite element method without any artificial diffusion, then we obtain a solution on the left. And again, showing here in this figure here is again the error field, right? And that's pretty much zero. In fact, I think the only way why this is not, the only reason why this is not exactly white, exactly zero, is purely because of export and visualization. Typically, you can't really visualize quadratic functions in most visualization toolboxes. Visualization always works with linear triangles. So you always have to project on some other mesh, and I think that's the only reason why this is not exactly white. Yeah, so according to all the theory, you can obtain the exact finite element solution of this problem. Now the same thing is not true from our streamline artificial diffusion. This is our, I still write Upwind diffusion, I should maybe say streamline diffusion. This is the solution that we would get with the streamline diffusion. Now it might look quite similar to the true solution on the right, but actually if you look at the error graph, then you find that there are certain bubbles inside of the domain, right? We have again this completely blue, so everywhere negative error, meaning that our finite element method is over predicting the solution. Everywhere we get sort of bubbles. Now, this might not look like a huge problem. The solution still looks quite similar, but this can lead to all kinds of problems if we want to make sure that certain quantities are maintained over time. Then we don't want to add any diffusion that's not absolutely necessary, because this will slowly start to kill all the oscillations that might actually be physical. Now, other reasons for why we don't like variational inconsistency are that we rely on this in all kinds of proofs of error convergence, of stability analysis. Variational consistency is not something that we're willing to compromise on. So whatever kind of finite element method we come up with and that we want to publish and use, it has to be variationally consistent. Which means that we actually can't use the stuff that we've built so far yet. The streamline artificial diffusion is variationally inconsistent, and that's not something we're happy with. Now, actually, all is not lost. So we can make a pretty straightforward change to our formulation to actually make this variationally consistent. And we can do so by kind of zooming into this additional term again. And something that I already pointed out in the previous video is that the thing that we're adding here, this a dot gradient of phi, is something that shows up in the partial differential equation already, right? So let me rewrite the partial differential equation. The partial differential equation was a dot the gradient of phi minus the divergence of kappa times the gradient of phi is equal to f. And if kappa is constant, then this can be rewritten as slightly simpler, kappa times the Laplace operator acting on phi. And what we see is that this additional term involves a section that also shows up in our partial differential equation. So thereby I propose to do the following. I propose to add also the following terms. And of course I'll have a reason for this, but let me first write down the additional terms. So I'm going to add some terms again that look like this. Tau times f minus kappa Laplace of phi a dot gradient of w. So my suggestion is to add this term on top of our streamline artificial diffusion that we've developed so far. Now, do I have a physical reason for this? No, not really. So why am I proposing to do this? Well, if we now rewrite both of these terms, so if we rewrite both of these terms, then we can see that they are actually of the following form. I think I want to have a minus here. Yeah. Okay, so then they'll be of the following form. They'll be of the form tau times a dot gradient phi h minus kappa Laplace phi minus f a dot gradient w. And maybe I should again highlight here, I'm using again the notation where we're simply replacing all our integration symbols by these L2 inner products, right? I hope that was clear, where the subscript omega means that we're performing an L2 inner product on the domain omega. So whatever I've boxed here in green can be rewritten as what I have here in the bottom. Why is that so interesting? Well, this is precisely what we call the residual. Or depending on the paper that you write, sometimes this is called minus the residual. Yeah, so the residual is defined as the right-hand side f minus whatever we have on the left-hand side in the strong form of our partial differential equation, which we typically write as simply L times phi, with this being our differential operator. So we see that if we add now these new terms to our streamline artificial diffusion, then the additional term that we add compared to the Galerkin approximation is actually something of the form tau times the residual, or minus tau times the residual, times a dot gradient w. Why does that fix our problem? Well, the issue was that if we substituted the true solution into the weak formulation, then in the Galerkin approximation that was satisfied, but in the streamline artificial diffusion problem or formulation, it was no longer satisfied. However, the true solution satisfies that the residual is equal to 0. Which means that the additional term that we're adding is actually equal to 0 for the true solution. Right, so just to make this very clear, the new formulation is going to be a dot gradient of phi times w plus kappa gradient of phi gradient of w minus tau times the residual of a w, or a gradient of w, and that's going to be equal to f w. And now this is something that is variationally consistent, right? So if we substitute the true solution, then the residual is 0. So this additional term is actually 0. And the remaining terms were simply the Galerkin approximation, and that was variationally consistent. So this is variationally consistent. So it's variationally consistent, and it has a streamline diffusion effect. And why am I saying that it has a streamline diffusion effect? Well, again, one of the terms that we still have in this formulation is this term that we specifically added to fix our problem. The additional terms, something that we maybe can look into a little bit. Let me answer my phone. I hope that doesn't happen again. So the additional terms, for the linear basis functions, you can already see that the second derivatives are actually 0. Yeah, so then for linear basis functions, even this contribution here doesn't do anything. And if we also have a 0 right-hand side, so f is equal to 0, then also that one doesn't do anything. So for linear basis functions with a 0 right-hand side, the new variationally consistent formulation is precisely the same as simply a streamline artificial diffusion. So stated differently, for linear basis functions and a 0 right-hand side, the streamline artificial diffusion is actually variationally consistent. But this is sort of a generalization. So this new formulation is a generalization of the streamline diffusion method in a variationally consistent sense when we're using higher order basis functions, so quadratic, cubic basis functions, or when the right-hand side forcing is non-zero. Now this method has a name. This is the streamline Upwind Petrov-Galerkin method, or SUPG. Now if I use that method in my numerical experiments, I'm actually not sure if I even added that picture. Yeah, okay, so this was with the SUPG formulation, and in fact I'm getting the exact same result as the one for the simple Galerkin approximation in this case. Again, because for the Galerkin approximation, we have the true solution, which means that the residual is 0, which means that the additional term that we're adding in SUPG gets cancelled. And that's precisely what we want. We want something, we want a stable method with maybe some additional terms, right? The SUPG term in this case, but that actually becomes 0 if we don't need it. And it only helps us if it is needed. And again, this one actually falls within the same class because my f was 0 on the right-hand side and I was using linear basis functions. So where I was calling this still the streamline diffusion before, this was actually an SUPG formulation. That's also how I actually obtained this solution field. So then let's also take a look at the convergence graphs. This was for the blue line, again, was for the simple Galerkin approximation, where in the beginning we had this very, very large error. And after we added some additional diffusion, we got an error that was okay, right? Again, this light, this yellow dot right here, that would be this solution field. But now we're adding, and the problem was that leveled off because the physics were incorrect, so we could use something, artificial diffusion that was also scaling, but it's not so nice because again, it's acting in all directions and it's variationally inconsistent. And this is now the line that you would get if you also add SUPG, where we see that in that pre-asymptotic range, in the large error range, we're able to reduce the error very significantly, but it also converges in the way that we expect. So that's kind of what we've built up so far. Going from artificial diffusion to streamline artificial diffusion to variationally consistent streamline artificial diffusion, and that's Streamline, Upwind, Petrov-Galerkin. Now I can almost not overstate how important this method was. This was proposed somewhere in the 1980s, and this was really the method that made finite element technology applicable for fluid mechanics applications. Before then, it was practically impossible to get good solutions with the finite element method, stable solutions that you could rely on with any kind of pre-existing technology. And SUPG was really the thing that kind of changed the story there. I think if you look at the original article from 1983, I believe, by Thomas Hughes and Brooks, then that's one of the most highly cited articles in all of finite element technology. Yeah? So that's I suppose a clear illustrator of how important this method was when it was first proposed. Now, nevertheless, it's only one of the stabilized methods, and we'll actually in upcoming videos take a look at a couple of other ones. And the general idea, however, is that we'll actually work with a formulation that looks like the one that we have over here. So a stabilization parameter multiplied by a residual multiplied by some operator here. And then we'll actually find that we can actually play around with this operator here on the right side of our inner product and get different stabilized methods. So that's what we'll do in some of the subsequent videos. Okay, thank you for your attention.